In Chapter 3, we talked about valence bond theory and how much easier it made our lives by simplifying molecular orbital theory. Valence bond theory is an important lie that allows us to understand lots of things about molecules fairly simply. Nevertheless, it's still a lie. Mostly, it lies about things like electron delocalization and resonance. Another way of thinking about the problems with valence bond theory is that we'll have issues if 3 or more p orbitals are next to each other. One of the simplest examples is the allyl cation, which has 2 resonance structures. Valence bond theory predicts resonance structures, but not the resonance hybrid, which is more representative. If we think about bonding orbitals using valence bond theory, we'd be tempted to give 1 pi bond and 1 empty p orbital. But we know from the resonance hybrid that this isn't the case. In this chapter, we introduce a qualitative way to think about the molecular orbitals from p orbitals. First, we know that molecular orbitals will be created from the atomic orbitals of different atoms. We know that we'll end up with the same total number of molecular orbitals as we mixed of atomic orbitals, and that they will be different energies depending on the overall in-phase, or bonding, and out-of-phase, anti-bonding interactions they have. The more nodes they have, the higher the energy will be, and the more out-of-phase interactions, the more nodes. And finally, linear systems will have all of their nodes symmetrical. This is a lot, but it will make more sense when we talk about a specific molecule. Let's look again at the allyl cation. We know that we have 3 p orbitals. The simplest and lowest energy arrangement will be with all 3 of these orbitals in phase, no nodes. The highest energy arrangement would be with everything out of phase, 2 nodes. The middle should have just 1 node, which we know needs to be symmetrical for this linear system. So we have 1 node on the center atom and 2 p orbitals that are essentially not interacting. These are not independent p orbitals, but pi molecular orbitals that look like this. So overall, we've taken 3 p atomic orbitals, mixed them, and made 3 molecular orbitals. If we start out with the actual allyl cation, we know that we have 2 electrons in the system. We also know that the 2 electrons will occupy the lowest energy orbital available, so they will both be completely bonding and completely evenly distributed through the pi system. On the other hand, we can look at the allyl anion in a similar fashion. We know that we have 4 electrons in the system. The first 2 are shared equally over the whole system, and the last 2 are localized on the terminal carbons. They are also the highest energy, and therefore the most reactive. This method of analysis continues to give us interesting results with larger molecules. Butadiene has 4 atomic p orbitals that all can line up and conjugate as well. While we normally think of butadiene as 2 double bonds separated by a single bond, this is clearly not the case. A single bond in ethane has a much longer bond, while the butadiene, quote, single bond, unquote, is actually much more similar in length to a double bond. We can see this a little when we think of the weak resonance contributors that have a double bonding character in the center. But these seem unstable, and we'd underestimate the contribution of these contributors without molecular orbitals. Let's together build up the molecular orbitals for butadiene. It has 4 adjacent p orbitals. Try to draw the lowest and highest energy molecular orbitals first. The lowest energy orbital should have no nodes and look like this, while the highest energy molecular orbital has nodes between every single atom, 3 in total. The remaining molecular orbitals should have 1 node for the second lowest energy and 2 nodes for the third lowest energy, and will be arranged symmetrically, like so, and like so. If we let our book draw the fancy pictures for us instead, we can see that the lowest energy electrons are actually shared across the entire molecule, and only the second molecular orbital has them in discrete double bonds. If we try to identify electron occupancy in these molecular orbitals, we can see that the bottom 2 molecular pi orbitals have electrons, as well as, of course, the sigma orbitals below them. All the orbitals above have no electrons in them at all. The molecular orbital of the lowest energy gives properties that we wouldn't otherwise expect, including some rigidity around the center single bond that prevents it from rotating, and of course, shorter bond length and more overall stabilization of the molecule. Delocalization can also occur in rings, as we know from benzene, but we get more than just the usual stabilization from delocalized bonds. There is something unusually stable about benzene. This is why we obsessively define benzene as not being an alkene. It doesn't go through any of the same reactions that alkenes go through. If we really push it, we can get a reaction with bromine. We need a catalyst, but benzene won't add both bromines. It only adds one and substitutes a bromine for a hydrogen rather than adding two bromines like we saw in an alkene. Notice that the pi system remains the same in this example. We see this stability another way when we compare the heat of hydrogenation for 3 cyclohexenes with that of benzene. Benzene releases significantly less energy and needs much higher temperatures to react in the first place. If we think about the stabilizing factors of the pi system, this makes some sense. The pi stabilization lowers the energy of the reactant, so the change should be less significant. This makes even more sense when you try to identify benzene's molecular orbitals. Again, the lowest energy is easy. Everything is in phase. The highest energy has everything out of phase. But notice that the nodes run through the entire ring. There are only 3 total nodes. This means that there probably need to be 2 molecular orbitals with just 1 node and 2 molecular orbitals with just 2 nodes. The first of the 1 node molecular orbitals is straightforward. One side is one phase and the other is the other phase, with a node right down the middle. The other 1 node molecular orbital has the same energy but looks a little different. There are also 2 2-node molecular orbitals, for a total of 6 molecular orbitals from the 6 p orbitals. These are drawn at roughly the right relative energy levels, which happen to be in the shape of a benzene. The nicely drawn pictures from your text might be more appealing to look at, but they're essentially the same. At this point, we can begin to see why benzene is so extraordinarily stable. The p orbital energy is drawn as a dotted line right down the center of this diagram. Ethene would offer moderate stabilization for each individual pi bond that's formed, but benzene has a much more drastic stabilization from its all-in-phase molecular orbital. The second and third molecular orbitals are both more similar in energy to individual pi bonds and have the same energy as each other. They're degenerate. But the all-in-phase molecular orbital is more stabilizing than any single pi bond could be on its own. We might think that this is true for all conjugated rings, but we see something very different with cyclobutadiene. Cyclobutadiene actually has 2 different bond lengths, and although the distance between atoms can change through equilibrium, these bond lengths indicate the molecule has 2 different types of bonds rather than some sort of resonance. We also see that cyclobutadiene actually reacts more readily than an individual alkene rather than the other way around. You try to draw the molecular orbitals for cyclobutadiene first, and then we'll go over them together. Again, it's easiest to start with the most and least stable because it can let you know how many orbitals with each number of nodes there are in the middle. Pause and then give it a try yourself. The lowest energy molecular orbital is all in phase, and the highest energy is all out of phase, 2 nodes straight through the molecule. That means the other 2 molecular orbitals will have 1 node each, like this or like this. Again, the shape of cyclobutadiene matches the shape of its molecular orbital energies. We know that this is a 4-electron system, and we can see a pair of electrons occupy the fully bonding molecular orbital, and also 1 electron apiece occupy the non-bonding orbitals. Benzene and cyclobutadiene are entry points to talk about aromaticity and anti-aromaticity. Benzene has a much greater stabilization, or much lower energy, than expected because of the additional stabilization of its molecular orbitals. We call this aromatic. Cyclobutadiene is actually higher energy than we'd expect from a molecule with two double bonds because two of its electrons are not at all stabilized. We call this anti-aromatic. We can also have non-aromatic compounds whose bonds behave just like normal double bonds or simple conjugated bonds. For example, double bonds that are separated by an sp3 hybridized orbital or linear molecules would be non-aromatic. We could draw out the complete diagram for every compound we think might be aromatic or anti-aromatic, but you can also use a shortcut. Huckel realized that in a fully conjugated pi system around a ring, meaning that every member of the ring needs to have a p orbital, certain numbers of electrons were always aromatic and certain numbers were always anti-aromatic. Aromatic compounds always follow the rule that they can have 4n plus 2 pi electrons. N in this case is any integer 0 or greater. So if n is 0, 4n plus 2 is equal to 2. If n is 1, 4n plus 2 equals 6. So a molecule can have 2, 6, 10, etc. pi electrons and be aromatic. Similarly, anti-aromatic compounds always have 4n pi electrons. So 4, 8, 12, etc. Any other number of electrons or other types of system is non-aromatic. Notice this fits for benzene and cyclobutadiene. Benzene has 6 electrons in the cyclic pi system and is aromatic. Cyclobutadiene has 4 electrons in the cyclic pi system and is anti-aromatic. If we want to get an idea of the relative energies of the pi molecular orbitals very quickly, we've already hinted at a method while we went through the benzene and cyclobutadiene examples. The Frost method suggests that the molecular orbitals will be in the same shape as the molecule, provided we orient the molecule taller than wide with one vertex down. The energy of a normal p orbital then should be directly down the center of this diagram, and each vertex would be a molecular orbital. Try it with naphthalene, the molecule that's shown. It has 10 molecular orbitals. One is going to be the lowest energy, and the one is going to be the highest energy, and everything else should be in pairs. 5 of the molecular orbitals will be below the energy of the p orbitals, and 5 will be above. But since there are only 10 electrons, they all occupy the stabilized molecular orbitals of this aromatic compound. Easy peasy.